So today's topic is going to be digital theater design. Okay, so we have learned quite a few technicals to be able to design and apply theater on different scenario in the practical aspects, such as shaping the noise or get rid of noise of original audio, and it's certainly one of the most important element of the DSP. So I think before Easter break, I did talk about digital theater in terms of its structure. So, well, digital theater can be represented as various different structure. So such as a kind of sort of flow diagram, because literally what digital theater does is to take input signal and apply various delay line, multiply by different coefficients, and then mixed with different delayed channel, and multiply different amplification or attenuation factors signal stream and synthesize the final signal. Then that's basically digital theater. So you can view on digital theater as different process. So in this diagram is what I basically Google searched digital theater in the image section. Those are come from the first page. It will look like extremely confusing because it has so many different form and the way to express it. So hopefully you get some basic idea of digital theater from my last lecture session about how the digital theater structure is. So I think the way you guys understand digital theater has some advantage, because I always compare the digital theater as some sort of audio routine kind of a routing process. For audio engineer and music technicians, they always need to dealing with multiple channels, and sometimes you mix these two channels, sometimes you apply different effects with channel and make final mixing. Yeah. So this analogy can be applied to a digital theater really. Just imagine you got one channel of audio coming and you split into multiple channels, and sometimes you pass any delay line, different delay, and you apply different, audio effects. We can't apply audio effects. Basically, we apply different amplification, and then you get out of one as the final mixing, which basically is input signal mixed with their own alternatives, own modifications. Then that's basically digital theater. I mean, okay, that's kind of an analogy. I'm not sure if you appreciated that or not, but at the end of the day, that kind of one channel is probably one strip in your DAW or workstation. So yeah, so those are the representation in terms of the signal flow, but then we have the mathematical function to represent the digital theater. So in general, let's summarize the most important two digital theater type. They are FIR theater, stands for finite impulse response theater, and the second one called IIR theater represents infinite impulse response theater. The difference between these two theater is basically FIR theater has not get any feedback loop within the structure, or from the mathematical formula point of view. I mean, the first expression was from the structure point of view, signal flow structure point of view. From the mathematical formula point of view, the FIR theater calculate output signal only from the input signal and the previous input signals. So we can simplify the FIR theater, generalize the FIR theater as the first equation here. This is FIR theater equation. So Yn representing output signal, X something represent the input signal. Okay, so within the bracket is index, which basically indicate the time of the sample. Normally, n representing the current sample. If you say n minus something, that means the previous number of samples, buffered past sample. So basically here is n minus k, that's indicating k is variable. So it actually, the output signal is calculated from various past samples, apply with also not just the past sample, but also applied a factor dk on that. So certainly for each different past sample, you apply different coefficient. So this is FIR structure. So this structure tells us the filter only calculate using input signal. So this finite impulse response, because if your input is finite, the output is going to be finite, because there's nothing more information you can get from the finite input. However, for IR filter, which is the second form, from the structure-wise, what IR filter does is it has a feedback loop within the structure. You still calculate output signal from input signal, but there's advantage of a digital system. You can keep the buffer of the previous output signal. So in that case, your output signal is not only calculated by a previous input signal or current input signal, which is same as a FIR filter. In addition, this is addition, it also takes count into the previous output signals. So you basically buffer the output and you to be used in the future. So in that case, it might end up with an infinite loop, because your output signal is going to feedback the system again and again. Certainly, when we design IR filter, the algorithm will make sure the output going to fade out to zero. Otherwise, you will create this positive feedback effects, just such as when you set up any kind of a PA system. Yeah, so you microphone pick up with the speaker, so it will get a positive feedback even you don't have any sound, because the sound will be amplified by itself. Okay. So last session, we focused on the difference equation expression. Well, I have to say that it is a difficult subject because the digital filter can be representing as different form. And the most easy form for program to understand is this difference equation. So because it only involves the output signal y and index n, which indicates the number sample, and coefficients. Those coefficients can be real number. When you have a specific filter, it will become a specific number. Then you have input signal xn minus 1, which is representing past sample, past 2 sample, and you have yn minus 1 representing the past output sample, and this past output sample 2 sample times ago. So this equation is very easy for people to understand as well, for in terms of from engineer programming point of view. But the problem is the property of the filter is hidden. We are not sure how we can judge this filter, if this is low pass, high pass, band pass, whatever. So to be able to do that, we need to have, there's a mathematical way, which is be able to analytically determine the type of the filter. This analytical approach is Cauchy transform. And there's a way to determine the type of filter is called frequency response. Okay, so that's slightly complicated topic basically, but we're not going to focus on maths because we are mainly focused on the practical aspect, but we just quickly go through this. So mathematician has introduced a factor called Z. In DSP, it's always appeared as Z power minus 1 as this factor, or minus something. Well, 1 is just exponent. You can have different exponent. But Z power minus 1 is a element, is a fundamental element of this Z transform. It representing a delay, one sample delay. So by doing that, we can converting the difference equation with the current sample multiplied by a delay factor. So the delay factor represented as is represented as Z power minus 1. So if you have 2 samples delay, it will represent it as Z power minus 2, and so on. So the number of samples delay will be converted into the exponent of this Z factor. So hence you can actually convert the difference equation into this called Z transform. The beauty of this mathematical tool is to be able to eliminate any explicit past input sample and output samples. So the equation, the end form, the eventual form of this equation has no longer involved any past examples, past samples, because you can say you need only yn, which represent the current output, xn represent current input. Everything else has been encoded. The time element of this filter has been encoded into this mystery Z factor. So rearrange, that will give us a general form of transfer function, which basically tells us a moment of the current output of the moment of input has a relationship which described by the right side of this equation. So this right side equation has no y or x, which basically means no input output involved. So this is independent of any input and output. Hence, this representing the structure or the property of the filter. So to decide what filter it is, you only need to decide what are the coefficients and how the structure is. I mean, structure basically is simple structure, just numerator, denominator and numerator with multiple terms of Z power something. It can have longer terms, but this is just second order. Okay, so by doing that, actually you can derive the frequency response in analytical form, because what is Z in the frequency domain is actually equal to e to the power of j omega and t. So this is how that is defined. It involves the natural logarithm base e, which is constant, like pi. I think this is probably 2 point something, 2.14. J, which is imaginary part, well, complex number. Omega is your frequency. So omega is a frequency in angular form, is equal to 2 pi f. T is your sampling period, 1 over fs. Again, it's still complicated. That's why we not directly use frequency-based expression in digital filter. We encapsulate it in this factor Z. And also it is, I have to admit, very abstract, because we have the frequency on the exponent level, and also it's a not a real number. I mean, in terms of a real or complex number, it's in imaginary imaginary exponents. I once been puzzled quite a lot about this number. I don't understand what physical meaning about an imaginary number at exponents. Yeah, we can understand 2 to the power of 2, but I can't understand what is 2 to the power of j or 2 to the power of I, isn't it? We can understand 2 to the power of 2. Basically, that means 4. But what is 2 to the power of j? Thank you, Tom. E is 2.71828. Yes, I can remember wrong. I thought it's 2.14. It's 2.7 something. Thank you. Yeah, E is a constant. You can actually 2.71828. It's probably like pi. It's going to be infinite long number. This is a magic number of universe. Any kind of exponential, for example, humans population increase rate is something to do with E. That's why we call it natural logarithm. The name comes with meaning. It is representing loads of natural phenomena. This is E. I mean, you can find the derivative or some knowledge about this. The beauty of this is this basically inherently has both sine and cosine part. If you have an imaginary number in exponents, you really wouldn't understand in the normal way as a normal, 2 to the power of something, or power exponent expression. You ought to convert that into both sine and cosine using Euler function. Euler function. So if you search Euler identity, Euler function. So it basically Euler function. Sorry, it's very hard to write on the mouse. Maybe I'm spelling wrong anyway. So if you search Euler function or Euler identity, it's basically combine 3 essential numbers in the universe into one equation, which is 1, 0, pi, and E. So those kind of thing. It's beyond my comprehension anyway, but it's very interesting anyway. Okay, so what really tells us is this expression actually contains the frequency, frequency element. So hence we be able to, for example, giving any frequency f equal to 0, then 0 hertz, f equal to 1 hertz, and so so then we can have every hertz we will have corresponding omega angular frequency. Then we'll be able to calculate a real number for given frequency. We can calculate any real number for given frequency by finding the absolute number of this expression. So if you have fixed f, then omega is decided. If you have fixed sampling frequency, then t is decided. E is constant. So we'll be able to, and the whole expression is a complex number, but by doing absolute number of this complex expression, we can get a real number. So for each of the frequency, we can get a real number. So this is frequency. So each of the frequency, we put it into the equation, we get a number. And then if we connect this number together, this is representing your magnitude. We get this filter type of curve. So that's how the filter curve derived from analytical point of view. All right, or no matter how complex, but you sure by logic you will find this type of result, isn't it? So you got any f will give a result. We also have a phase response, because complex number, not only, for example, if this is complex domain, this is number, complex domain number. So you have imaginary x and you have real x. So the complex number is following the space of the complex. So you not only have the magnitude, which is distance between that number to the original 0, you also have the angle, which is representing the phase. It is important sometimes for digital filter to look at phase as well, because that basically means you altering different elements of the signal differently. That's called phase response. Well, basically means if you're looking at a signal as a combination of sine waves, different frequencies. So the phase response means this filter will also delay those sine wave, cosine wave slightly different, because a phase shift of sine wave, cosine wave, you can regard it as a phase delay. All right. So if you have sine wave, if you delay the version of sine wave, is basically a phase shift. So all these are linked together, but there are loads of details. I mean, I have to say, it's interesting to actually explore more. All right, so they're just like an expansion of a little bit more about what I just did in previous slides. So what basically says is how to calculate absolute number. So to calculate absolute number, a real number of that is basically saying I want the real part of this square, imaginary part square, and a square root. So the result will be a real number. Okay, so any questions so far? I'm going to move on. All right. I think that you will have a question. I still have a question after 15 years of on DSP. Right. Okay, so let's go. So how can we, so we now have this, we understand the digital filter and we understand the frequency response. Why we need to do it? Why are we doing it? The reason we're doing that is because the engineer really likes the performance. So this is like we're saying that it's one direction, isn't it? So we come from the direction from the transfer function, which is hz, we could call hz, to the frequency response. So if this is low pass filter, something like that, yeah. So we just went to the journey from a transfer function to the frequency response. But for you guys, you doesn't want this journey very well. You probably want, but you're not using this journey quite often. You want a journey which is backwards. You normally say, I want a low pass filter, give me the digital filter. All right. So this is not reverse engineer, but the engineering approach. This is engineering approach. I want a filter. I want the filter looks like this, a low pass, cut everything under 1K. But I want you give me a digital filter. With the mass approach, is like this, isn't it? So you have the digital filter analyze what filter like that. So the filter design is basically does this job for you. This is filter design job. So we get this filter response and then we work out what filter looks like. Okay, so let's go to the next slides. I hope that makes the concept a little bit more clear. It's very complicated concept. It's very hard to sometimes to explain. Okay, so let's look at the common way to do it. So there is a block diagram. This block diagram, I think I get from the MATLAB help file somewhere. So the engineering approach of filter design. So how can we design filter? So the way to design filter is sort of like any software engineering project. You have to specify what the software like. All right. So you want this user interface. You want the software to be response every certain second to check this, check that. So the performance measurement of the software or user specifications. So for filter is more about performance specifications. So when we have a performance specification, then we design the filter, try to fit that specification. In loads of time, the algorithm will directly output filter but sometimes the process is iterative. That basically means you come back to design another filter and try if that fit for your performance and so on. So once you got the filter designed, then you also looking at from the theoretical world to the practical world. Practical world means when you design the filter, this filter perform very good, but it basically need a 128 long coefficients precision. And in any kind of DAW, you probably talk about 64 bits or 32 bits computer software. You need to put into a finite word length. And sometimes if you say, I want my digital filter to actually work on the a guitar pedal or kind of a small hardware gadget, then you need to talk about software hardware implementation, stuff like that. Okay, so the first thing is understand the filter specification, filter performance specifications. So we're going to go through this very quickly because you guys are expert on that. Yeah, probably better than me because you use this quite often in your area. So first of all, we define, so in terms of this, we have to have some common terminology. So we talk about low pass filter, high pass filter, band pass, band stop. They're arbitrary shape of the filter as well. So those are general knowledge of what we want to refer to. I'm not going to talk too much about this. Okay, so any digital filter also has their specific. So this picture exists on both domain, analog, digital. They all have this type of different low pass, high pass, band stop. But for digital filter, you normally have the specific performance measurement, which we call performance specifications, because of the artifacts. At the start of this lesson, I mean, of this module, I always said the DSP, the whole science of DSP really is to understand error and the noise, because we are trying to simulate this sophisticated analog infinite world with limited digital world, digital computer. So everything we consider in DSP essentially is error. So we then, for example, have low pass filter. And then in digital filter, we normally have this, some sort of we call a passband ripple. So passband ripple, in most cases, smaller is better, right? So this indicate we want a low pass filter, but because the limitation of my digital filter, we introduce some fluctuation or distortion within the passband. We have transition band. Analog system has transition band, which is very natural. You can design very steep digital filter, but your digital filter probably not be able to realize. For example, you need 1,000 or even 10,000 and millions long filter to be able to have very, very sharp digital filter. And then you also have a stop band attenuation, which basically, because you also introduced a stop band ripple. Stop band ripple basically means you not eliminate any frequency totally at stop band, so you end up with certain stop band attenuation, not very good. Maybe if you want to eliminate that frequency. Oh, I mean, by the way, there are filters it's not just strictly you want to pass band, stop band, such as the EQ. You really just want to colorize the frequency, enhance bit or reduce bit of the frequency here and there, which we're going to talk about next week. But this week is basic filter stuff. Design a desired curve of the filter, which defined with certain number, certain region, and the filter realization ideally, or filter design algorithm ideally will fit within the error region of the filter you designed. So think about this. Then if you think back to the SP2 we used so far, you said, some sort of A pass and A stop. Those are the error tolerance you give to the filter design algorithm. So Next, what I'm going to talk about is how I have to say, there are thousands, 100 filter design method. If I haven't do a proper research on how many number of different filter, but every year there are filter design method papers. Some are small modifications, some are totally new. I mean, even now people using artificial intelligence, machine learning, or different optimization algorithm to design filters. It's still the active area. So I'm going to give a talk about a fundamental couple of basic filter design method. Still people doing PhD or research on this area, but to understand those fundamental filter design method is a foundation for any advanced way. So that's why when you're doing MATLAB, you probably will say you can select a range of different methods. Those are classical methods. Okay, so we're going to first talk about FIR filter design. FIR filter, IR filter are two types of filter. FIR mostly used in audio in terms of if you want to separate frequency elements. A typical application such as crossover. You send one low frequency to a low speaker, high frequency to your high frequency speakers, stuff like that. So FIR filter is very ideal to do a low pass, high pass classical filter. So when we design FIR filter, the typical way is called sync window filter design. So we look at what is the mean. Okay. So first of all, let's look at an ideal low pass filter. What is ideal low pass filter? This diagram shows an ideal low pass filter. Frequency response of ideal filter. The amplitude is a linear mode rather than dB. So you have amplitude 1 means you are not altering any kind of energy, the energy of those frequency. Then you have a cutoff frequency at FC. So after cutoff frequency, any frequency greater than that, the amplitude will be 0. So all the frequency eliminated. Below cutoff frequency, you have amplitude 1. This is called break wall ideal filter. All right, so what we can do is to say, let's take, this is frequency domain. We take an inverse FFT. Inverse FFT is basically saying, I want to find the time domain signal of that. So then use that time domain signal, we'll be able to use that time domain signal as filter kernel to convolve, do a convolution with signal. We will end up with this ideal filter. Okay, so where's my last slide? Okay, here. The mouse is always moving twice too. Okay, so then the people find to be able to do the inverse FFT with ideal filter, which I'm not going to do that. If you can find there's textbook of the describe of all the steps to take this as inverse FFT. You will end up with a specific shape of the time domain filter kernel. We call time domain filter kernel. So there are specific time domain filter will looks like this ideal filter. So this time domain filter is we call a sync function. A sync function basically looks like a sine wave, but it has a symmetrical sine wave around certain point. So at the center of the symmetry, they has amplitude 1, and the energy just fade out on the both side. So it's basically defines, there's a special symbol for that called sync. Sync x is defined as sine x divided by x. Sine x divided by x. So this is a specific or single function. You probably not very as common as other trigonometry functions. So the property of this function is at when x equal to 0, when x equal to 0, it defines the value as 1. Otherwise, this function has no meaning. We can't have anything divided by 0. But we specifically say when x equal to 0, the whole thing is equal to 0. So when x increases this number, or both sides, negative or both positive, this number will become smaller. So that's single function. So to be able to get to the ideal filter we showing in the first picture, what we need to do is to have this single function, but with infinite length. So this actually theoretically demonstrates impossible to have an ideal filter to be able to implement in a real practical sense, because you need to infinite length of this single function. So the engineer take a simple approach. The simple approach is basically say we have a limited memory space in computer. We just need to store a limited number, but we cut the single function as some sort of a certain shape, just as a symmetry. So we cut left and right number of samples same. So we call truncate single function. So we only truncate certain part of this single function, such as basically same as yesterday we talked about windowed FFT. So we take a window of that. So it will still perform as a low pass filter in this case. But in this case, the low pass filter is going to be non-ideal. It introduced the pass band ripple and the stop band ripple and the transition band. So really it's trial and error. So we basically take certain part of that and then we end up with certain non-ideal filter. So sometimes you said, I do want more smooth transition band. I don't care, sorry, I do want more smooth pass band, but I don't care have a little bit longer or larger transition band. So then another technical has been invented to actually, so scientists find the problem of this error, one is because we have limited kernels, we call filter kernels, because we cannot have infinite one. Second is because we have sudden change on the both end, because we truncate it. So the sample is sudden change from 0 to have some value, from some value to suddenly to nothing. So then try to create some sort of a smooth kernel. People invented a couple of functions called window function. So those window functions are named after the scientist, Blackman or Hamming window. So those windows are very widely used in audio processing. You probably, in some kind of DAW, you probably can select different window. So window can be described in certain functions. I have some function here. So here is a Blackman window function. Is defined in the digital domain. Those are the coefficient, specific coefficient to result in a Blackman window shape. Essentially, what the window function does is just smooth the single function and then produce some sort of improved low pass filter curve. So you can see this curve has been improved, has the pass band ripple has been removed, but the sacrifice is you have probably longer transition band. Okay, so there are different type of windows. So what we do is just like envelope. We've done this envelope exercise. Yeah. So what we do here is basically say we apply this as envelope to the filter. So we create this filter kernel, new filter. So I have the some MATLAB demo here, but I'm not going to run MATLAB. So this is produced by MATLAB. So we can create a single function in MATLAB easily, and then we truncate. So this created by quite a long single function, try to simulate infinite. So the process is then you truncate it is a single function, and you apply a window. Here's honey window is again another very popular window function. As long as you keep the length exactly same as the sync function, then you multiply them, you create this called windowed sync function. So this can be used as a low-pass filter kernel. So people might wonder how this links to this filter equation stuff. So I'm going to just quickly show. So you do I have any equation here? Not really. Okay. So when we say yn equal to b0 xn, so this is a filter equation we studied before, b1 xn minus 1. Yeah, I'm going to just Peter asked what does the filter kernel mean? Yeah, so I'm going to just explain what filter kernel mean here. Okay, so this is what exactly I'm trying to say here. All right, so this is the filter we actually familiar so far. All right, so and I just write a couple of line here, and then dot 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 dot. You can have some to bm and multiply by x m minus m. So Peter, you understand what is field coefficients now. So those are the field coefficients, yeah? So we're familiar with this equation in terms of field coefficients, yeah? So this field coefficients also is called field kernel if this is FIR. So this is basically called field kernel, the coefficient alone. I understand that this is very bad domain. Different terminology come up. So where this coefficient in this single function, when we design filter, we have this graphic representation. How that link to coefficient is basically here. The first number, first point, the value of the first point is B0. Then we have B1, then the third one is B2. So those filter kernel is basically a collective of the filter coefficients representing as a graphic way. So the last one is your BM. So the digital filter can be, represented in the both mathematical formula as well as a graphic way. Is that okay? Yeah. So the problem, not the problem, when we're doing digital filter, because in FIR filters, sometimes the filter kernel is quite large. Hence, look at this, is 100 coefficients. So we cannot really, it's not very convenient to write that in the equation because we have to write all the 100 coefficients. So we just take the coefficients and plot the coefficients in the graphic way and save that as a filter kernel. So I hope that's clear, but certainly we can discuss in the future if you still not very clear about that. So what is the FIR filter design process really is the most popular one is called equal ripple filter design. Equal ripple filter design has fairly complicated algorithm, but in short, what it does is has a try and error. So it follows those couple of steps here. What basically says is you guess what filter coefficient number. So here we got 100 number. So if you want to design filter, you first need to estimate how many number you need. and create a single function and apply a window and say if the filter works. If it's not, then we redesign it until it fit for your specification. That's really it. So iterative algorithm, filter design algorithm is not an equation. It's a piece of computer software for FIR filter. For IR filter, there are equation way to do that, which we talk about next week. Okay, so the simple step I summarize in this slide is saying how we design it is we say, let's give a filter design specification. We want a certain type of filter. We want passband ripple no bigger than that. And we want a stop band attenuation, must bigger than this dB. So those are filter specifications. So from this specification, we can estimate the best FIR filter order. There are equations to do that. Then using different methods and iterative process to find the filter to be able to fit. Because even you estimate order, you might not be able to, use your filter when you design might slightly unfit for the purpose. So the filter design, the filter order estimation equation, my PhD student work on this quite a lot. So it's fairly complicated way, but they are famous equation. This is Kocher and Ribena function. We don't need to go to detail. Basically, you can understand this is the relationship between how many order of the filter kernel, which is how many coefficients you need, and the delta 1, delta 2 is passband ripple, stop band attenuation, delta F transition band. So all the right side of the equation is filter specification. This is just a function of passband, stop band, ripple, and this again is passband ripple. So everything here, delta, this is special function also is expanded here. So everything to do with filter design specification can come up with a certain number, for example, 100. So you basically, this equation give you a best guess. If I have 100 number of single function kernel, truncate 100 number, you might be able to achieve a filter with this transition band, with this pass band ripple and stop band attenuation, stuff like that. Well, there are also other simplified method. Kesa actually invented a filter method called Kesa window because his guess is pretty much close to the final result. You can directly use that number as filter design. I'm not going into that detail because those are not very important in terms of nowadays for you guys doing filter work, because we are normally using filter design package. Okay, so just a few words about when we now have a low pass filter. We now know how to design a low pass filter. Although it's non-ideal, let's come back to the diagram, but we can design some sort of low pass filter with not very ideal, but very good, fit for useful. And we got a set of method to be able to, a software algorithm to be able to find a best fitting filter. But the filter we need is more than low pass. So we have different type of filter. So there are methods to convert low pass filter to different type of filters. The specific interesting method are called spectral inversion or spectral reversal. We look at it generally. So again, those are some discoveries of some DSP scientists. So for example, we have a typical original low pass filter. On this part, the upper part of this diagram showing a typical low pass filter kernel and the filter response, low pass filter, yeah. So we can convert this low pass filter to a high pass filter, flip top for bottom. So flip up and down, so we can create a high pass filter. To do that, you just need to do some magic operation on the filter kernels. So the filter kernel is being changed by description here. So change the sign of each sample in the filter kernel. So if it's positive, become negative. If negative, become positive. And second, add 1 to the sample of the center of symmetry, because the single function normally have a peak point at the middle. So if we change the sign of the every sample, this one become here initially. So then we add 1, basically bring that sample to the positive point. So the adjusted kernel will produce a flipped spectrum. Don't ask me why. It just happens. So scientists discovered this. You can experiment that with MATLAB code as well. And then second one is you can flip the low pass filter left and right in the center of the symmetry. So if you flip low pass to left and right, so you become high pass filter. But in this case, the center of the symmetry you flip around is certainly a quarter of sampling. So the maximum frequency is half sampling frequency. So this is quarter of sampling frequency. So it depends your sampling frequency, your high pass filter will be different. So in this case is by changing the sign of every other sample in filter kernel. So we keep the center of the kernel unchanged, but change the coefficient sign. If it's positive, become negative. If negative, become positive. Just keep it original. So for example, all the odd number, first, third, fifth number, we change in sign. So we can actually flip the spectrum from left and right. And then you can also combine different filter into different shape. For example, you can combine bandpass filter by cascading a low pass and high pass filter with an overlap bit of the spectrum being a bandpass. The cascading process is also equivalent to convolution. So you got filter kernel of this and the filter kernel of that, then you can convolve them. And if you do a parallel link, so if you got a signal coming to 2 different filter, one is low pass, one is high pass, but they don't have overlap. So the common rejection part will become band reject filter. So you parallel connection to filter, you create band reject filter. In the way, the band reject is basically say this filter in mathematically just add them together. If you mix this filter together, you can create band reject, depends on original 2 kernels. So for this, you can, from the simple low pass filter, you can create any different filter by manipulate the filter kernels in FIR. Okay, so well, there are some other method called arbitrary FIR filter design. Is directly taking the frequency response of filter, stuff like that. So I'm not going into too much details. Okay, so couple of slides. I think we run out of time now. So, but I think just a couple of slides talk about this. Is in MATLAB again. I give you loads of theory. Is probably confusing. It's quite a complex area, but it's start point. So you understand the basic idea, at least intuitively. I hope understand how filter design works. But in the modern engineering era at this time, we have a very good, engineering software to help us. In MATLAB, basically there's 3 commands to help you: fdesign, design, fvtool. I think we touched a bit on practical already. So those basically is implement those algorithms I talked about in the slides, maybe with advanced alterations. Okay, I think I'm going to shut up now. I think that's about an hour time. So I hope you get some interesting aspect of the filter design. It is a hard topic, and it's very hard to deliver in the pure lecture. But next week we're going to look at IIR filter design, which is more links to more engineering in terms of audio and music engineering aspect. That's probably kind of more close to the area you're doing. So I think that's an important lecture. I suggest everybody turn up to understand. We're going to introduce a bicoder filter design, or IR, and the EQ. All right, so thank you very much to attending my session, and have a good break. And if you have time, please also go to my register and sign the name. I still need to report to university about attendance. Thank you. See you next week.